Today, we test one idea with clear and simple thinking. Could a self-sustaining population of megalodons survive in the deep ocean? No movie myths. We will use biology and basic math, calories, oxygen, prey density, and evidence. If the numbers fail, we will show you where they fail. If any door stays open, we will show you why it stays open. If a giant apex predator still hunts in the deep, that is more than a fun fact. It touches American fisheries and shipping routes, Navy operations, and even the undersea cables that carry financial trades and your nightly streaming. Confirmation would rewrite risk models in a single day. Here is what you can expect from this episode. First, the real megalodon, based on fossils and modern science, what it was, how large it was, where it lived, and what it hunted. Second, the deep ocean itself, temperature, oxygen, and how life survives without light. Third, the energy bill for a predator 50 to 60 feet long. Could the deep ocean afford that cost? Fourth, the kinds of evidence that could prove or disprove survival today. Environmental DNA, bite patterns on whale remains, and sonar signals that are worth a second look. Finally, a clear verdict on how likely survival is and what would change if it turned out to be true. Our rule of thumb is simple. Extraordinary claims deserve ordinary math. We will keep estimates conservative, cite what is known, and mark what is uncertain. Curiosity drives us forward. Skepticism keeps us honest. Take a quick gut check before we dive deeper. What are the odds in your mind right now? Very low, low, or still open? Hold on to your number and see if it changes as the evidence builds. One more note before we begin. We are not here to make you fear the ocean. Fear is cheap. Wonder is better. The ocean feeds our coasts, carries our trade, powers our weather, and still holds most of Earth's undiscovered life. If Megalodon is gone, the deep ocean remains the wildest frontier you will never hike. If Megalodon somehow survived, the deep becomes even more interesting and far more complicated. Let us start with the only solid ground we have, the fossil record and the real animal it reveals. What we can measure about its size and its bite.
Thick like a wedge. By comparing tooth size and shape to living sharks, researchers estimate a total length of about 50 to 60 feet for very large adults. Think about a yellow school bus, end-to-end with a pickup truck. That is the kind of scale we are discussing. Body mass is harder to pin down, but even conservative models place the animal in the tens of tons. This was not a larger great white, it was a different class of predator. Bite power next. Engineers use tooth dimensions and jaw geometry to model force. Results vary with method, but most land in the same neighborhood. A bite measured in many tons of pressure. Enough to crush ribs and split thick bone. When you look at fossil whale bones with clean semicircle gouges, you are seeing the calling card of a giant with a very efficient toolkit. Growth and life history. Megalodon did not reach full size overnight. Growth ring studies on vertebrae suggest steady growth across many years, like the slow climb of a mortgage balance in reverse. Young sharks likely lived in warm, shallow nurseries, calm bays and lagoons that offered gentle water and smaller prey. As they grew, they shifted to deeper and more open water to hunt larger animals. Range and climate. Fossils show a near-global distribution in warm and temperate seas. The Atlantic and the Pacific both hold tooth deposits. So do the Gulf Coast and the eastern seaboard of the United States. During the Miocene and Pliocene, oceans were warmer on average than they are today. Warm water favored a big body that could cruise long distances and strike hard. Diet and hunting style. Look at who was common in those seas, and you meet the main course: early whales, dolphins, and large fish. A smart way to hunt a strong swimmer is to hit the softest points, the fins and the belly. Many fossil whale vertebrae and ribs carry scars that match large shark teeth. An ambush from below or from the side is the likely move. Strike once to disable, circle back, finish the job. Scavenging also played a role. A whale carcass is a windfall of calories, and big sharks do not waste windfalls. Body design. Like some modern mackerel sharks, Megalodon may have had limited warm blood features that helped keep muscles and eyes a little warmer than the surrounding water. This regional endothermy gives better sprint individuals to the same place.
Competition and hierarchy would decide who eats first. Scars on living sharks show that serious animals tolerate rough company when the payoff is large. Fossils cannot capture those moments, but the logic of energy does. Why this foundation matters for our question: everything you just heard points to a design built for warm surface waters, for fast ambushes, for large calorie-dense prey, and for nurseries near shore. If we are going to ask whether a population could survive deep below the light, we have to carry this blueprint with us. Big body, big energy needs, strong but not unlimited thermal control, and a life strategy that depends on finding large prey often enough to pay the bill. Hold these anchors as we turn to the second pillar, the deep ocean itself, its cold, its pressure, its oxygen, its food, and what those conditions do to even the strongest hunters. The deep ocean and what it demands of any giant hunter. Begin with the shape of the water world. Near the surface, sunlight powers life and vision. This top layer is the epipelagic zone. Below it, the light fades fast. The twilight zone begins, and then the midnight zone follows. Farther down lie the abyssal plains and finally the trenches. Each step is darker, colder, and poorer in easy food. Temperature falls as you leave the sun. Surface waters in many seas feel mild to the touch. A few hundred feet down, the water chills like an ice chest. In the deep, the temperature sits in the 30s and low 40s Fahrenheit for long stretches of the year. Cold slows muscles and digestion. Cold also narrows the window where a large animal can move at top speed. Regional warm muscle can help, but it is not a magic shield. Pressure rises with every 33 feet of depth. At trench depth, the pressure is crushing by land standards. Skeletal bone can resist better than air-filled lungs. Cartilage is flexible, but it still faces the same physics. Every heartbeat and every tailbeat must work against a heavy liquid world. Oxygen is not the same everywhere. Some layers hold less oxygen than the surface. These oxygen minimum zones form in many oceans and can stretch for hundreds of miles. Animals that live there move slowly, sleep often, or travel through fast. A giant warm predator burns more oxygen than a small cold one. That creates a night toward the surface to feed and sink by day to hide. This is the largest migration on Earth by numbers and by weight. Predators follow that wave. Squid and many fishes live on this schedule. A hunter that wants to eat them must climb and drop with the wave, or ambush along the slope where the wave brushes the seafloor. Navigation in a world without light uses other senses. Many deep animals sense faint water movement. Some sense tiny electric fields. Some see only in flashes of blue-green light. Bioluminescence is common in the dark. A large, fast approach can set off a chain of sparks and give away the attack. Stealth is harder for a giant body in a light-sensitive world. Now place a giant shark in this setting. A body 50 to 60 feet long wants space to accelerate. It wants prey that is fat in calories and large enough to be worth the chase. It wants oxygen-rich water when it sprints. It wants temperatures that do not drain its strength. It wants a search pattern that regularly finds big meals, not just crumbs. The deep offers two kinds of routes to those needs. First, the margins where the deep meets the slope of the continents. Here currents compress life against the wall. Upwelling and eddies can hold dense schools and squid swarms. Second, the vertical highway of the daily migration. An ambush from below at the edge of the wave could work when the math adds up, but the math is strict in the deep. Every mile travelled costs energy. Every long sprint in cold and low oxygen costs even more. Misses are expensive. Winds must be large and frequent enough to pay the bill and leave a surplus for growth and for raising young. Breeding adds another problem. Many large sharks use warm, shallow nurseries that protect the young and offer small prey. The deep has no safe coves. Pressure, cold, and low food density are harsh on small, growing bodies. For a giant shark to live mostly in the deep, it would still need access to nursery zones that fit its young. Migration can glue these pieces together. A large shark could spend time near rich coasts and island chains where food is dense, then dive along slopes and into basins to scavenge whale falls or to target squid and schooling fishes during their nightly rise. Long loops around gyres and across basins could link these stops. Modern sharks already show this pattern on a smaller scale.
cash in on rare jackpots. Could a whole breeding population live there most of the time? Only if the energy math and the nursery problem both find workable answers. Keep this map in mind as we move to the next question. What does the energy bill look like for a predator this large? How much food per day or per week would it need, and can the deep ocean pay that bill with any consistency? The energy math for a giant hunter. Start with a simple truth. Big bodies pay big energy bills. Every tail beat costs fuel. Every missed strike wastes fuel. Survival is a spreadsheet that never stops updating. We need rough numbers, not perfect ones. Think in ranges and orders of magnitude. Picture an adult megalodon in the 50 to 60 foot range, body mass in the tens of tons. Even with a slow cruising heart and cold water helping to save energy, a hunter this large still needs large meals at reliable intervals. Use two guides from living animals: large sharks that feed in big bites and large marine mammals that dive deep for food. Great whites do not nibble all day. They score a rich meal, then coast for days. Sperm whales burn serious calories on every dive. They make the math work by finding dense prey fields again and again. Build a conservative intake model in your head. If a giant shark weighs dozens of tons, a single successful strike on a small whale or a big chunk of blubber can deliver hundreds of thousands of food calories at once. That one win can cover days or even a couple of weeks of basic needs. But the ocean does not pay on a fixed schedule. 2 dry weeks and 1 bad chase can erase the margin fast. Energy density matters. Blubber is the gold card. It is rich in fat and easy to process compared to bone. Muscle is decent. Gelatinous prey like many jellies is poor. To keep a giant engine running, you want fat, heavy targets. That means whales, dolphins, large tunas, and big squids when they are dense. Cold water helps and hurts. Cold lowers the base metabolism of a fish. That is a savings. But cold also reduces maximum power and slows digestion. If a giant shark sprints, large moving body. Population math sits on top of the individual math. One animal can get lucky for a season. A population must get lucky often. Enough food must be available for males, females, and the young over years and decades. They must find that food across huge distances and harsh seasons. If the average intake falls just a little short, the line collapses over time. Nursery needs press the budget further. Young sharks cannot chase big whales. They need sheltered places with smaller prey and warmer water. Shallow bays and estuaries are the classic option. The deep ocean cannot offer that. So even a deep adapted adult would still require a life cycle that touches productive shallows. There is one more lever that can make the math work. Predictable aggregation points. Edges where currents trap prey. Fronts where warm and cold meet. Seamounts and continental slopes where the vertical migration compresses. If a giant hunter can learn those calendars and ride them like a trucker rides interstates, the cost per meal drops and survival odds rise. Put the parts together. A 50 to 60 foot shark can, in theory, balance the books if 3 things line up. First, frequent access to fat-rich prey or fresh carrion. Second, travel routes that keep search costs low by following predictable prey highways. Third, seasonal access to warm, shallow nurseries for the young. If any one of those 3 breaks, the red ink spreads. Too few fat targets, too many long empty miles, or no safe nursery, and the population math turns against the giant. This is why the deep ocean is a hard home for very large fish. The energy is there, but it is spiky, not smooth. It arrives in bursts and in patches. To live on bursts, you need either a small, steady body or a giant body with extraordinary luck and perfect timing over many years. Hold this frame as we move to evidence. If such a predator were balancing the books in modern seas, we should expect certain fingerprints. We should expect traces in the water. marks on prey, and patterns on instruments that do not care about rumors. Biology and thermal limits for a giant shark. Begin with how big sharks make heat work for them. Some mackerel sharks keep parts of their bodies warmer than the water. This is called regional endothermy. Warm muscle and warm eyes give value is locked up for longer. Big predators prefer a cycle of hunt, then digest in slightly warmer layers. They do not want to sprint hard in very cold, low oxygen water and then sit cold and empty while the gut moves like molasses. Add oxygen to the picture. The deep ocean has layers with lower oxygen than the surface. A large, active fish needs a high flow of water over its gills to keep pace. Cold water holds more oxygen than warm water, but deep layers with low mixing can still be tight on supply. Short sprints may be possible. Long fights are harder. Recovery will be slower and must happen in better water. Pressure climbs with depth. Sharks do not have air bladders, so they avoid the squeeze problems that hit many bony fish. Their big, oily livers add lift and help with buoyancy. Cartilage is flexible. Even so, every piece of tissue works under high load at great depth. Moving and turning costs more under that load. Any injury is harder to shake off. Look at known divers among sharks. Deep-living species like the blunt-nosed sixgill and the Greenland shark cruise slowly and spend years growing. Their pace is low. Their bodies are tuned for cold, dark living and long life. Fast, heat-aided sprinters like makos and white sharks are built for mixed waters and quick ambushes. They will make deep dives, but they do not live most of their lives in the abyss. Senses matter in the dark. Sharks can sense faint electric fields and pressure waves. They can see enough at low light for ambush near the surface. In the deep, the rules change. Many animals flash bioluminescence when disturbed. A large hunter can light up that alarm cloud by accident and warn the prey. Stealth for a giant body is never free under those rules. Feeding style must match the toolkit. A giant ambush shark thrives on one heavy strike into fat-rich prey. That strategy is perfect in clear, mixed waters around dense prey fields. It is harder in cold layers where prey is spread thin and where speed and vision drop. You can scavenge a whale fall and win big, but falls are rare on any single route, and you cannot build a stable life on luck alone. Thermal geography also matters. Fronts and eddies create stair-steps of temperature. A giant shark could ride those edges, hunt where warm and cold meet, then rest and digest a little higher where the water prey density is high or when carrion is fresh. But cold, slow chemistry, low oxygen layers, high pressure, and thin prey fields all squeeze the margins. The body can cope for a time. The population must cope for generations. This does not close the door completely. A small number of giants could live a mixed pattern. They could migrate long distances, use coasts and islands for steady meals, then take deeper routes to scavenge when a whale fall is near. They could hunt along the vertical migration when the nightly wave stacks prey against slopes. For a stable breeding population in the true deep, the hurdles remain steep. Heat balance, oxygen limits, and the nursery problem pull in the same direction. They push the design back toward the layers where light still fades, rather than the zones where light is gone. Hold this biological frame as we look for fingerprints. If such animals were out there today, we would expect traces in the water, patterns on instruments, and marks on prey that match a very large and very specific set of jaws. Fossils, isotopes, and modern traces. Begin with the ground we can stand on. Fossils tell us where and when an animal lived. For Megalodon, the clear signals are teeth and a smaller number of vertebral discs. The youngest reliable layers that hold its teeth point to a disappearance by the end of the Pliocene. That is long before human records. This is the baseline most scientists accept. There is a complication called reworking. Storms, currents, and geological shifts can lift old teeth from older layers and drop them into younger sediments. A tooth found in young sand does not always mean a young animal. Dating must rely on the age of the layer that formed with the tooth, not only the sand that now holds it. This is why single finds without a secure layer do not change the big picture. Isotope clues add texture to the story. Minerals in teeth record hints of the water an animal lived in. Ratios of oxygen isotopes can reflect temperature ranges and movements between warmer and cooler places. For Megalodon, the isotope signals align with a life spent in warmer waters with excursions into cooler zones. They do not show a species adapted to the permanent cold found in the deep. Now look for modern traces. A living giant leaves fingerprints in 3 broad ways.
Signal that points to a living megalodon. Marks on prey are the second line. Large sharks leave semicircle gouges and broken ribs on whales and big fishes. Scientists compare spacing and curvature to known jaws to infer likely culprits. Modern strandings sometimes show big bites, but those patterns fit known predators such as great whites and orcas more often than they fit a jaw larger than any living shark. When measurements are taken with care, the fits point to living species, not to a ghost giant. Instruments form the third line. Sonar and other acoustic tools see shapes in the water column. They also map dense schools and single large targets. A true animal the size of a bus at hunting depth would appear as a strong, moving target and would repeat in the area if it hunted there often. Claims surface from time to time, but they do not repeat with the consistency needed to build a case. Most unusual echoes resolve into schools, topography, or whales after closer passes. Cameras help, but the deep set's harsh terms. Light is scarce, visibility is limited. Remote cameras see long stretches of nothing and then a burst of life. A few minutes of footage are not a census. Baited cameras at depth do capture sharks, squids, and scavengers on whale falls. So far, nothing on those tapes requires a predator larger than the biggest living sharks. Put these strands together into a fair test. Fossils say the line ended by the close of the Pliocene. Isotopes say the animal favoured warm waters, not the permanent cold of the abyss. Modern traces that would be expected from a regular deep resident are missing. No repeated eDNA, no consistent bite patterns beyond known species, no instrument records that hold up under repeat surveys. This does not prove a negative in the strict sense. The ocean is wide and our eyes are few, but science weighs patterns over time. When the expected signs of a large regular hunter do not appear across many methods, the likelihood of a surviving population drops. Hold that probability in mind as we move forward. If a giant predator were present today, often enough to sustain itself, we would expect to find at least one reliable thread and follow it. In the next part, we test one more angle. Could the prey base and encounter rates in modern seas feed not just a single lucky animal, but a whole breeding population over many decades?